1800s, scientists were really interested in understanding how the gases of our planet behave. The problem is, it seemed unpredictable. There's too many variables all in play at once. You have pressure, volume, temperature, gas, the amount of gas. And so in order to try to understand how these gases behave and the relationship with pressure and volume, they imagined an ideal gas, which is where we're going to start off our discussion. The ideal gas law pretends that we have a gas that behaves in a predictable fashion, and then we can start to understand the relationship between pressure, volume, and temperature, as well as the type of gas. So let's imagine that these kids are my gas molecules. Now, molecules are really, really small, so we measure them in moles because it's just big clumps of molecules. And then I'm going to say that the volume is going to be the container and the structure of the container as well. And then we're going to say this radio is the temperature. Because if I turn up the radio, I put these kids in the room, I put the radio in the room, and I blast the stereo, they're going to start dancing and moving around. And that movement, or the amount of chaos that occurs inside this room, is going to be equivalent to our pressure. So let's take this gas law, pressure times volume equals the number of gas molecules, and it's in relationship to the temperature. And the R is just a constant that we use for converting this measurement. But this is pressure, volume, the number of moles, and the temperature. So if I take these kids, and let's see, there's 1, 2, 3, 4, 5, 6, 7, 8. There's 8 kids here. I put them in this room, and this room can't expand, right? It's not like a bouncy castle where it can expand. This room is a fixed structure. And then I put the radio in here and I turn it up, they're going to start moving around more. And so if this was able to expand, it would, but it can't. So you can see it's kind of like pressure ventilation and volume ventilation. In this, when we control the amount of volume, the pressure goes up. However, if we can't control the amount of volume and it's able to expand, well, then we're going to see that it actually does expand and we get an increase in volume. But there's still just 8 kids in there. That hasn't changed. It's just how much they're moving around. And so that introduces us into Gay-Lussac's law. So this says that
the pressure of a gas is directly proportional to its absolute temperature, provided the volume remains constant.
So in these oxygen cylinders, they can't expand. So if we put these in different extreme temperatures, we put it in the hot sun or we put it out in the cold, we're going to see those behave in different ways, right? So turning up the temperature is equivalent to turning up that radio. So what's going to happen? Well, all the kids inside this oxygen cylinder start moving around more and we get an increase in pressure. Now, does that mean that you have more oxygen in this tank? No, not at all. It just means that those molecules are moving around more. Now, if it's cold, it calms down. And so you actually see that pressure decrease. And so this is in a fixed container, right? This is a container that can't expand, it can't contract. However, if you look at something that can, like let's say a glove, you're going to see that if it can expand, hot air likes to make things expand. You can take some hot water, some boiling water, put it in like a soda bottle and put a balloon over top of it, and it'll start to expand because it becomes less dense. However, if you blow up a balloon and put it in the freezer, you're going to see that contract. So this is how I